for quantifying concentrations of different elements in seawater. And he made his name in sort of determining the profiles of these different elements in seawater and how that was influenced by biogeochemical processes and so on. He made his name as a chemical oceanographer for the last 30 or 40 years, largely by using electrochemical methods. And the strength of it was, unlike some method like ICP mass spectrometry, it's also very sensitive, where you have huge potential matrix issues, like in seawater, the main one being salt, right? That interfere with measuring. You have salt in the parts per thousand range, and you have some elements you might want to measure in the parts per trillion range, so 6 orders of magnitude lower, right? Rather than have that problem like you do in ICP, in this case, if you put in seawater, right? And seawater doesn't really interfere with this kind of reduction process, right? That high matrix. So it was relatively independent of those kinds of sample matrices. The only thing that does interfere is if you have other things that may coat and glom onto the electrode and reduce the electrochemically active surface area of the electrode. Right? And of course, electrodes can be made out of a number of different materials. In the case of the electrode for the glucose sensor, they're essentially made out of like a carbon electrodes, flexible carbon electrodes. And carbon electrodes, of course, carbon is a very hydrophobic molecule, right? And so they're very easily fouled in some settings by organic materials that get on there and glom onto the carbon. A lot of electrodes in these cases are either made out of they have graphite electrodes, essentially carbon-based electrodes. They have electrodes made out of mercury, electrodes made out of silver chloride in the cell. So they can make electrodes out of different materials to try to minimize or get around potential interferences. But in general, the method is far more robust and resilient to matrix issues of a sample than some of the
Before you change that, I have a question.
Yeah.
So are the potentials going to be specific to that element? For example, you have like tin and lead up there that differ by 0.01. So if you set it the potential to negative 0.14, is it like if we had a solution of tin and lead, like because the potential is higher, are you going to end up reducing both of those things?
So, that's a good question. So this answers your question. So you say, all right, I have a solution, and this is the reality, right? You don't just have a solution of cadmium, obviously, right? So you have a solution that has a lot of things in it. You've got lead, and maybe you've got tin in there. And you can say, all right, I want to measure all of these in the same sample, in the same measurement scheme, analysis program. So I'm going to apply a potential to my working electrode that's greater than the reduction potential needed to reduce all three that's on the electrode. So for those three, what would they be? So cadmium we know the reduction potential is, the reduction potential is what? Okay. And for lead, the reduction potential is what? Negative 0.13? And for tin, reduction potential is what? Okay. So now, which one of these? Let me just say, which one of these? If you were to, just so we're going back, if we were to make a cell with two different electrodes, choose for this list, which one of these could we use as the electrodes in terms of the half reaction to generate an electrochemical cell? Cadmium makes sense, and probably either of these, right? These are really close. It wouldn't be a very, very effective electrochemical cell because the reduction potentials are so close, but let's read it from this, right? So if we made the electrochemical cell out of the electrode of cadmium and electrode of tin, which one would be the anode, which one would be the cathode? Which half reaction has a higher affinity for electrons based on the reduction potential?
The more positive one's going to be the cathode, right? So the cathode in this case would be.
Is that what you said? Okay. This would be the anode. Okay, now if I'm doing stripping voltammetry and I wanted to measure all three of these metals in the solution, what would I do? What is one example that I could set the electrical potential of a cell in which to reduce or plate all of these cations onto the electrode? That's an example. What reduction potential could I apply to the cell in order to facilitate the reduction of all three of these?
0.26 volts.
You need something higher than 0.4.
Higher than negative 0.4? If I want to reduce these onto the electrode, right? So now I want to set the potential of my cell to drive the reactions this way.
I need to be more negative than negative 0.4.
So would you want to set it more negative? Because you'd want to be reducing these at the electrode?
You'd want to make all those the more positive values, so you want to apply a potential that's more negative.
So, so what would you say you want to do those?
Because if you keep the pattern going this way, and then the cathode going this way.
Okay, so we have our working electrode. We're going to change our little dial here to change the potential. Right? And if I want to reduce these three metals onto the electrode, what do I do to the potential? Well, do I need to change the potential based on each of them?
No, if you want to do the same thing to all three, you would either just set it, you'd set it to a range, well, you set it below negative 0.4, right?
Less than.
Less, yeah, more negative than.
Right.
Less than.
So you'd want to set the potential to be more negative
The most
than
negative one.
this one, right?
Yeah.
And if the potential is more negative than this one, then the reaction, meaning the reduction here, will be spontaneous. And since these are less negative than this, these will all get reduced. If you set it to say, I'm going to set it in this example, maybe I want to set it at maybe, negative 0.6 or something, right? Something more negative, and that's going to facilitate the reduction of all three of these metals, right? Because they're
How would you distinguish each of them?
not there yet. Okay. All right, so now I have this voltammetry scheme. So now I know these reduction potentials of these three metals I want to measure. I think they're in my sample. I know the reduction potential at which these metals are going to be reduced, right? Or oxidized, which direction you're going. And in my first stage of a voltammogram, say, which I'm going to generate, this is what this is for the non-extrusion voltammogram. I'm going to say, right, and I'm going to first apply a potential to my cell, and I'm going to apply it for a length of time in order to reduce the metals onto my electrode, which is that reaction at the top. Now I've got these three metals. So in our example, we say, let's set it for negative 0.6. I could say, I want to measure everything in there. So I'm going to make it a really negative potential, and I've said that. And I'm going to plate out everything in there that has a reduction potential that's more positive than that. And I do that for some length of time. We've got a scale break here, meaning that you can do it for a long time, right? But it's a fixed amount of time. And then at some point in time, the program that I program in to the anisotropic voltometer is now going to change the potential at a given rate that I define, right, over time. And it's going to be set at some rate of, whatever I decide, that the instrument is going to change that potential. And now the potential is going to be going from strongly negative, it's going to change it now becoming more positive. And as that potential is scanning across the range that I set, as that potential reaches the reduction potential for each of these elements, it's going to get oxidized off that electrode. And as it gets oxidized off the electrode, say you got cadmium here, it's going to generate a current. And so if I look at the current that gets generated at a given potential, I know who that is. I know, in this case, it's cadmium. And the size of that current, the area here, is going to be proportional to how much cadmium was on the electrode surface that got depleted during this deposition step. So it's totally cool, because you could say, well, if I have samples that are really low in concentration, I'll have a really long deposition step and plate a lot of it on there, because there's so little of it there. And then I know the reduction potentials of these metals well, and I can scan that, the change in potential of the instrument in order to optimize detecting the elements that I want as they are oxidized off the electrode and generate current. And so you would get a stripping voltammogram, which is what this is, and you can notice the axes. So this is what you call a reduction, sort of excitation and stripping signal diagram. And on here, this is telling us, the experimenter, what we're doing, what we create. We would set this. We would say, I'm going to have a certain potential that I'm going to hold it for a certain amount of time to plate things onto my electrode, and then I'm going to have a certain amount of time that I change that potential at a certain range and a rate that I change that potential. So I program this in, and then I'm measuring this as a result of that. I'm measuring the current that occurs at a given potential. And this is the potential I'm setting that it hits there at a certain point in time. And this is the current that results from that. And when I look at this,
Time's out after like 2 hours.
does it?
It was like left on before.
Right.
Yeah.
So wrong.
That's right.
So you usually deposit all of the metals in your solution onto the,
Well, probably not.
but
Probably not, but we deposit,
part of that happens stepwise though, that's the stripping of the,
yes. So here we're measuring the current in amps. And this is the reduction potential. And you get then some. So maybe in this case we'd say, all right, this is, we know this was minus 0.4, that was minus 0. Was it 1.3? And the tin was 0.12 or 1.14. So this isn't the scale, obviously. But as I'm changing this, we would be relating that specific potential, of which things are coming off, and where they come off, where I get a current is what's allowing me to identify what that reaction is to that species. And And so what window just asks is how much in that cell, how much of the analyte actually gets played on the electrode. And there are a lot of factors that affect that. But most cells may be a volume of 10 mils or 50 mils, up, relatively small. And in most cases, if you wanted to plate out most of all that was there, you had to have a relatively very long deposition stage. Right? Because you have to allow, you have this electrode here, you have to allow the analyte in that solution to find its way over the electrode, and within that diffusible layer of the electrode in order to be plated on. And that typically take, 30, 40 minutes, to maybe do a substantial depletion of the analyte. It depends on what concentration it is. So if we think of the stripping voltammetry, we'd say, what's the advantage of that over like plating voltammetry? That'd be one thing that I might ask you. And what is the advantage of that?
You can concentrate it all before you test it.
So you can concentrate it before you strip it.
Yeah.
Before you strip it, right? You concentrate it, and so if you have the exact same program that you use for standards, so you put in a standard just like you do, and you generate a standard curve, just like you do everything else. But in this case, the standard curve that you're generating would be the concentration of your analyte that you place one at a time, not one analyte at a time, but one concentration at a time in the cell. You analyze it and then put the next standard in and analyze it. You should get a relation between concentration and the signal that was produced as a result of that concentration.
Is it just the height of the peak, or is it like a integral of the?
You can do either.
Okay.
So you could either measure just the peak height, or you can measure the integrated peak area. Usually people measure the area. And you get a standard curve of that, and then you do the same thing we've done for everything else. You then measure your sample, and you get a signal from your sample, you interpolate the concentration point based on that. And of course, it assumes that you're using the exact same deposition and stripping conditions for your standards and your samples, right? Because obviously if you didn't, then this relationship wouldn't apply to your sample. Okay. So one is the, okay.
Do you have to change the electrodes from them getting plated all the time?
I have slides of this, but I don't have it with me here. For the instrument that's in the classroom, there's a big reservoir of liquid mercury,
Oh, yeah. I've seen that.
which is not necessarily the safest. And that liquid mercury reservoir feeds into a apparatus and it's got a little capillary that feeds down here, and it's got some solenoids up here to control whatever you're moving down. And if you blow up the tip of that electrode that's inside the solution, it's got the capillary coming down, is the electrodes formed by dispensing a tiny drop of mercury. And a drop of mercury that's dispensed off there is calibrated, so when that solenoid clicks open and closed, it's calibrated so that that drop is probably about maybe zero, I'm just sort of guessing, 0.2 millimeters in diameter, maybe. Okay. And that 0.2 millimeters diameter electrode hangs, mercury electrode hangs there. And then you've got in that same, now this is in the cell, and in that same cell, you've got the reference electrode, also the counter electrode, completing the circuit in that cell. And then the potential you're applying is the potential between reference electrode, and this is now your working electrode, that hanging mercury drop. And so you can do some analyses with that hanging mercury drop until the sensitivity seems to start to drop because maybe it's getting foul with stuff in it. Then you just push a button and it goes, and it dispenses with the solenoid opening. Another drop, this drop falls to the bottom, and you treat a new drop. And you can generate thousands and thousands of electrodes because you got a lot of mercury up in that thing. And the downside is, all that mercury goes down here, and then at the end of the day, you've got to dispose of that mercury as a particle waste hazard. And so there's, you know, the positive is that it's a replenishable electrode, and that if the instrument is calibrated and performs properly, the size of that electrode is exactly the same each time. Because obviously, if that size of that drop changed from one sample to the other, that would be a change in the size of the working electrode, which you're oxidizing or reducing aniline onto, and you get different signals because the surface area is larger and you have more aniline variable because the surface area is larger. So it's important that the dimensions of that hanging drop are always exactly the same. And that's why, for the money in this stuff, the money that's used to purchase an instrument like this is not the electronics, because they're pretty simple. It's in some of the electronics and solenoids that are controlling how much mercury is going to put out, because that electrode is exactly the same size. So these are still pretty common to use because they're so cheap. The alternative is if you didn't have a hanging mercury drop, but you had, say, this silver chloride electrode or something that was a different kind of material, then you would have disposable electrodes that you would probably replace every day. Right? Okay, so let's go to stop now, right? We're a few minutes early. The key things that I want you to take away from this are understanding what reactions are occurring at the electrode for stripping voltammetry, where you are essentially varying the potential in the cell to oxidize or reduce, depending on whether you're stripping or plating, analyze it as the potential you set, and the current that results from that allows you to identify the analyte as well as the relative concentration of the analyte.
If the oxidation of the analyte increases as you decrease or increase the potential, so like for cadmium, right, you had a potential of negative 0.4 volts. As we increase the potential past like 0, right,
Increase positive.
increase positive of the volt supply, that would create a strong potential difference between the two. And if you're unable to completely get the plated material off the electrode, wouldn't that mean that you have contamination in the signal? Like, is it, because these peaks over here for the voltammogram are pretty sharp, but I'm just wondering if in practice they are actually that sharp, or if you have a lot of noise.
So there's several ways you could go. One is you could say, you're talking about how do I set this program. In this example, I had this linear function where potential is changing and a measuring device had a bunch of noise results in that and that specific potential.
Yeah.
And there may be something that has, like the example of tin and lead, where they have reduction potentials that are very similar, but they're only different by 0.01 volts, if I remember right? Well, in that case, you would want to make sure you're scanning very slowly, because if you're scanning too quickly, then you're going to start getting the tin, whichever one came first, the tin off, and then you're going to scan past that potential, then you're going to start, this is coming down, you start getting the lead off, right? So in that case, you would have a program, if you were really trying to measure tin and lead, those are some of the specific things you're interested in, you'd probably have a step program, rather than have a linearly declining function for a change in potential. You would say, I'm going to change the potential to minus 0.02 or whatever. It was a little bit more so that the lead wouldn't get oxidized off and the tin would. And you would try to separate those. Does that make sense? Yeah. I think that's what you're asking, right? How do you deal with things coming off at the same time or something? Yeah.
Yeah, no, it's also that, and the fact that if we can't remove all the plated material off of the electrode, so I would think that as you increase the potential, right, the potential difference between the two, you have a really strong oxidizing agent, or yeah, a really strong oxidization of the plated metal. The bigger the potential becomes, the more metal I would expect to come off. But I guess if not, more.
Is that true?
I would think so. If the potential is larger, then there should be a bigger driving force to oxidize the species.
That's right, but would that bigger driving force in terms of, well, so the reality is that bigger driving force doesn't translate into a greater signal or which is coming off because you're limited by the rate at which the electrons can be passed to the reduced species on the, or the oxidized species to the direction point. If you're actually going to oxidize off and measure the current from that, even if you have a large potential difference, there's a rate limiting step in the oxidation of the electrode and the movement of electrodes and then the movement of that away from the electrode. Okay. So you would not get you don't get a huge difference by really having a large difference in potential. All right, so let's stop here. So are there any questions about this? And
Yeah, so the reaction potential of a specific species would, on the bottom graph, it would occur like what, at the right of the peak, or like I noticed the dotted lines are to the right of both peaks. Would it, like, I mean, that seems to indicate that you would start getting an electrical current from that species before you actually reach the reduction potential of that species.
so this may not be exactly accurate relative to this. So here we're looking at cadmium coming off at point. They show it here on this one, the standard reduction potential of 0.4 volts. Right? And then you look at it in this example, which is right here. Okay. So this isn't calibrated. This isn't meant necessarily to line up, I guess. That's not, I'm guessing, right? This is in your book. Where you think like, why is, if the reduction potential of cadmium is way over here, why am I getting cadmium oxidizing here? Why would that be? If you go, with a potential that's more negative of all this, we have everything that's getting reduced onto the electrode, right? And so I think my thinking is that this isn't lined up exactly like it should be to match the reduction potentials. So that table that I had of reduction potentials isn't isn't paired with this information. So the reduction potentials that we're measuring in this case, gosh, I know exactly what measure that. Reduction potentials we're measuring in this case are relative to what?
Hydrogen.
Hydrogen, right? Okay. What if we had, this is actually a good point you brought up, what if we had, which is the reality, in the case of a stripping cell like that, let's say we have our mercury hanging drop electrode, and our work in our reference electrode is silver chloride, and this is mercury working electrode. So working electrode, the reference electrode. And instead of having a reference electrode that is hydrogen, based on the hydrogen half reaction rate, we have a reference electrode that's silver chloride. And what that does is then the relative difference between what's happening here, cadmium, getting oxidized, or reduced onto here, or oxidized off of there, the potential in which that occurs for cadmium is going to be a reduction potential relative to the reduction potential of silver chloride. And so if we look at silver chloride, where is that on this?
Right there, 0.22. Towards the bottom.
Right.
You just, it's like 4 up from the
On
bottom.
the side.
Near the bottom.
You go to the
Yeah.
Okay, thank you. Plus 0.22. Okay. So we'd have to adjust the reduction potential for the cadmium reduction by plus 0.22. And I think that's why, if you look at this, why it's not happening here, but it's happening roughly plus 0.22 over from there.
Oh, so it would line up with about the top of the peak.
Yeah.
Oh,
That's what it
okay.
should be. Not plus 0.22 volts away from this, so that would be 0.66. That's roughly, that's supposed to be this close. 0.62. If we actually do this experiment, that'd be something you have to do because you'd be getting reduction potential, you'd be getting peaks coming off of reduction potentials. It wouldn't match that table because in the case here, the reference electrode actually is silver chloride. All right. So we'll do a quiz on Wednesday. We'll do a little more biological chemistry, and then we'll be done. Exciting